Good afternoon, everyone. Welcome to the optional and final lecture for the course. Yeah, so today's lecture will be slightly different. We will be giving a very kind of quick introduction to object-oriented design. Okay. So far, so what we have learned is, so we have learned object-oriented features in C++. So basically, it's about implementing object-oriented programming or thinking in terms of object. Okay. And most of our things were basically solving problems which were like implementing algorithms which were taught in the related course, mostly fundamental algorithms. So many a times, so when you develop systems which are huge, particularly software systems, okay, it's not just having object-oriented programming features is not alone enough. You need to think that your software design or your software itself in an object-oriented fashion. Okay, so this is so what we are going to do is it's basically following a set of slides created by Ian Somerville, who is an author and software engineering expert in software engineering. Yeah, the main reference will be the slides by him, and in fact, I just basically copied content from that in a filtered fashion. I didn't take all the slides, and yeah, the main reference will be book on software engineering by Ian Somerville. So usually this content is, I mean, will be part of a course on software engineering or object-oriented design. Unfortunately, we don't have. So the perfect follow-up for the course, the lab course now is to think object-oriented design. So I hope I'll be motivating you to read it up maybe during summer or later on, okay, so that you have object-oriented thinking in mind. Okay, so it's basically complementing what we have done so far. Okay, so it's essentially the idea is to view a software design problem or software design as a set of interacting objects that manage their own state and operation. Okay, so in general, I mean the sequential, I mean the traditional programming, imperative programming, essentially it's like a flow chart would represent your software, right? Yeah. So there is no object. There is no, the whole system would be essentially a flow chart. It's basically based on flow. Whereas object-oriented view gives a fresh interpretation of this. It also helps, I mean, it's also practically useful. I'll tell you later, particularly in the distributed set. So the purpose of this lecture is just to give an overview of the object view of software development. Yeah, basically, I mean, formalize modules of OO design, how to make object-oriented design, but like I said, we in the limited time we'll just quickly rush through it, and also motivate you to learn and use what is known as Unified Modeling Language, UML. Okay, this is not a software. I mean, this is not a programming language. It's basically a design language. Okay, so when you design a system, say basically you want to develop a software for hostel management. Okay, so then so if you want to have purely object-oriented approach, then you need to describe the design. Okay, so you need to specify your classes, their interactions, and how they what is the inheritance structure and so on. So UML is a language for doing that. In fact, there is also a syntax-oriented UML. UML is a generic language. There is something called rational rows. There are also other verification softwares, which actually you can use UML to specify your system, and then it will verify if the system has any flaws and so on. Okay, so that is also something quite useful for software. We will not get into this verification part. Okay, so yeah, so let's just again be a bit more abstract than what we were. Okay, so let's start with the describing object-oriented design characteristics. Okay, so here the primary elements are objects. Okay, so briefly, objects are abstractions of real world or system entities and manage themselves. That is the main thing. Okay, so I mean In the C++ realm, we just said objects are basically instances of classes. So we just saw them as a data type. Okay. So rather in the design view, so what you say is they're basically maybe a piece of software, but they're basically abstraction of some properties. Okay. Only thing is they manage themselves. So that means they have data as well as functionalities. Okay. And objects are independent and encapsulate state and representation information. That is encapsulation of state and representation. That is, state is nothing but data. So representation information is basically implementations. That is functions inside it. Yeah. So one typical view that object-oriented designers take is you just imagine. So object is basically like a physical object, you can imagine. Okay. It stores some data and offers some functionality. Its functionality is nothing but a service. Okay. It's providing service to its user in the form of methods implemented. Okay. So that way it gives you this view. So every object is basically a distributed system. Okay. Sitting and it has its own data and it also offers functionalities. So how do you communicate? You make a request by making the function call. One way people formalize this is basically they say objects communicate by passing message instead of sharing data. So this is a drastically different view than the imperative program. Okay. So imperative program usually, I mean, the modular programming paradigm, what you have is basically modules which are functions. Okay. How do they interact? One function calls the other. Okay. But data has to be shared among all the functions. Whereas here, objects, they have their own data and they communicate. Okay. So that basically one object calls the function of the other object and vice versa. So, so this is called message passing. So the function call is called message passing. Okay. So objects communicate by message passing instead of sharing data. So whenever we use the term message passing here, we essentially mean function call. Okay. One major advantage here is the objects may be distributed and may execute sequentially or in parallel. Okay. So the moment you have object-oriented view, you can imagine an instance of a class sitting in some system, far off another class, instance of another class is sitting somewhere else. If they want to communicate, they just call function of the other class with each other. I mean, functions of each other. Okay. So that is how they communicate, and data are managed by themselves. So whatever functionality, so these they can run independently. So you can just imagine servers waiting to take requests. So that is a standard view in object-oriented programming. Okay. So yeah. So just to be clear, so we have that slightly. So whenever I say object here, I mean classes. Okay. Classes as well as instances, which is so in the class we said okay, class is a data type and then object is an instance. So here when we say object, we actually meant both. Okay. So yeah. So there's a slight difference in the language used here, but the viewpoint taken by object-oriented designers is something. Each class is an independent system. Okay. So it holds some data. Okay. Class or in fact instance of class object. Okay. It holds some data and it offers some functionality. So you make query to the system. Okay. Not query, you communicate to the system by calling their functions. But in a purely object-oriented sense, what they imagine is a program or your software system is essentially consisting of objects and they interact by calling each other. So it's not a sequential flow view that we take. Okay. So it's about the object interactions. So that is the main feature of object-oriented design. In this course, we only learned object-oriented programming. We didn't learn object-oriented design. So that means essentially what we did is we implemented classes for specific purposes and used them. That's all we did. We didn't really look from this perspective. So just imagine, I mean, so one way to see is like your current assignment or the previous assignments, you're using a lot of built-in classes already, right? Matrix, vectors, and so on. So you can just imagine, so matrix is an object, vector is an object. If you have graph, which is an object defined by you. Now you are declaring variables of each type, and then one function method in one class calling the other method. That's exactly what we meant by communication between the objects. Okay, so that's essentially it. For our applications, I mean, they are not so humongous, so we can't take that view right away. But in general, if the software system is huge, this view really helps. Okay? So this is a one pictorial view of interacting objects. So you can just imagine this is object 1, object 2, object 3, and so on. Each of certain class type. This is class 1, class 3, class 4, and so on. Okay. So now at some point this makes call to operations of this. So this is the interaction. At some point this makes a calls to operations here, and so on. So these arrows indicate interaction, but it does not tell temporally when. See, that is the main difference here. Okay, when you think object oriented, so the object design does not really specify the flow of the system. Okay, so that has to be done separately. It only gives you object view. So these are different classes and their objects. They interact in this fashion. What is missing is sequentiality. Which one will go first and how the interaction happens. Okay, so I'll also tell you how it is. I mean, briefly about it, but not much in detail. Okay, so object-oriented design basically like it keeps the sequentiality later. The sequentiality will be in fact done by the standard imperative program. Okay, for that you need a flow chart. But this only talks about how objects interact with each other. Yeah. So the main, I mean, this is part of any software development. Is one is analysis of the system. We basically analyze and decide on okay how to proceed or how the software to be built, and then design, come up with the so in this case object oriented, come up with classes, and then programming. So the last part is what we have seen so far. Okay, so basically programming. The design was essentially, I mean, it was not very sophisticated and it was already in the problem statement. Okay, so object-oriented analysis and design. So these are the three parts: OOA, OOD, and OOP. So what you have done so far is OOP. Okay, so OOA is concerned with developing an object model of the application. We'll see in detail, a bit more detail, what it really means. And then OOD, object-oriented design, is concerned with developing an object-oriented system model to implement the requirements. Okay. So OOA is essentially you want to identify classes. So what are the different classes and what is the inheritance structure? Object-oriented design is basically talking about interactions, specifying methods and then interactions between them. So implementation is using a programming language to implement this system, basically write a program, okay, which implements all these classes, methods, and so on. And then of course a main function which sequentially attempts to run the software. Okay, so okay, any questions? Yeah, so we need passing data. So you see passing data is essentially by they don't pass data per se. Passing data is through parameters to function calls. See, communication is basically through function calls. So passing data is through as parameters to function calls. Okay, that is say class A and class B, object of class A and object of class B. So to communicate, object of class A will be calling a method of class B. The data being passed is the parameters to the function. That is how it is done. Okay. So assumption here is there is no shared data as such. Okay. So we already know the difference between classes and objects. So classes are basically data types and objects are instantiations of it. Usually in object-oriented language, so people use the term object classes and templates. Okay. Yeah. Sorry, object classes and objects. Okay. So objects are entities in a software system which represent instances of real world and or system entities. Okay. Object classes are templates for objects, or in other words, basically classes. So they may be used to create objects. That means instantiation. And of course, object classes may inherit attributes and services from other object classes. So this is essentially what we learned. Only thing is the language is slightly different. So usually in software development, people use the term object classes. In C++, we said a class and then object. Okay, object classes here means a class. So template, not necessarily the generic programming template. So template is basically a class definition is called template in object-oriented design. Okay. In C++, when we say template, template is more like class template or function template, where there's a parameterization on the type. Okay. So, well, I mean, there's only when you read up object-oriented design, so you may have to keep this in mind. That's all. Okay. So, yeah, so I just took the formal definition of objects and object class. Okay, so it's just here. I'm not reading it out. Okay. So what actually is an object and what is an object class? So object class is class and object is object, what we have seen. But these definitions are important, particularly when you devise or when you design huge software. But mainly because you need a formal definition of what is a class, okay, to identify classes. Otherwise, it won't be very natural. Okay, so yeah. So yeah, the formal description is it serves as a template for objects. So includes all declaration of all attributes, services which should be associated with an object. Okay, but object is something that, say, car is an object. Okay, or student record is an object. Employee record is an object. So you can just see that all that will fit in. So what should be an object class or what should be an object should fit into this definition. Okay, so it's basically given for formalism purpose. Okay. Yeah. So now, so one important thing is, like, when you develop systems, software systems, okay, it may not be just implementing one algorithm. Maybe you're implementing 100 algorithms and then utilizing in some fashion. So you need a way of communicating your design. Okay. See, usually what happens is in most of the corporations, what happens is like software development. So there will be different teams. Okay. So not everyone will be implementing. There will be a team which actually does what is called as requirement analysis. So basically, I mean, for a company, suppose for a factory, you want to develop a software. Okay. First, a team goes there and takes out all the requirements that they need, that is the system requirements. So that's called requirement analysis. Once that is done, the next step is going to be design. Okay, so there are again two steps there. One is architecture, software architecture, and then or system architecture, and then system design. Okay, so the object-oriented design is only about design, not about architecture. So architecture basically abstracts out the functionalities. So design is what describes the system. Okay, and then implementation is the actual program. So all these are different teams. Okay, so you need formalisms to communicate between the teams. So for example, design team should have a formal system to describe their design. Okay, so unified modeling language is one such language. Okay, so yeah, so the need for having such a language, I mean, people realized it since the 70s, 80s. So people came up with several notations for describing object-oriented designs. In the late 90s or mid 90s, unified modeling language was proposed. It's essentially an integration of these notations. It describes notations for a number of different models that may be produced during an object-oriented analysis and design. Okay, and now it's a very, very common standard. So if you are doing an object-oriented design, so it's recommended that you use this language. Okay, like I said, language here does not mean so much of syntax. Of course, there are certain things that you need to keep in mind, but generally it's again about description of objects. Okay, so I'll give a simple example. Okay, so what it basically needs is, I mean, you need to describe all classes. Okay, and then you need to draw interaction diagrams between them. Okay, so how do you describe the class? You basically give the class name and then all attributes, that is all data that is being stored. Okay, and with their type. So name must be a string, address must be a string, date of birth must be date, employee number must be an integer, and so on. So here this data type is kind of abstract. What I mean to say is, like, it need not be consistent with any programming language. Okay, it could be user defined or intuitively defined. Okay, so for example, this status should hold these three values: current, left, retired. So this is not of any data type. Okay, so it basically specifies these are the values. Now when a programmer comes and implements, he or she will be choosing suitable data types for each of them based on that programming language. And then it should specify the methods. So for an employee joining the organization, leaving an organization, retirement, maybe changing the details, or could be transfer and so on. Methods could be anything. Okay, so UML basically has, so in UML you will be basically, when I say employee class, you should be specifying what are the data, that is attributes, and what are the methods or functions. Okay, usually people call it as maps instead of methods. Okay, yeah. So this is an example of UML description of class. Okay. Yeah. So now I'll briefly describe what do we mean by object communication. Okay. So one idea is, so you have, so say suppose in a system you have lots of classes. Okay, in our case, I mean, we had, I think, at most 2 classes in any programming assignment that we have given, right? I mean, it's not necessary that you just have 1 or 2 classes. You'll have lots of classes. So UML, what you do is you write classes. So basically, in a box, you create a class. I mean, write its descriptions, and then write their interaction, like is pointed out here. You draw their interaction. Okay, so this one interacts with this one interacts with this one interacts with this. It could be bidirectional also. Okay, so that is, so here basically it says that this class, one of the methods from this class calls a method from here. If methods from this class also calls method from here, then it will be bidirectional. Okay. Yeah, so UML has those features. You can start or describe a class. So description is essentially this way. Okay, so like I said, these are data types, need not be like consistent with any programming language. It could be user defined or slightly intuitively described. So for example here, and what you need to describe is communication between them, interaction between them, and for each of the methods you will have to specify what is its purpose. Okay, what is it doing. So this communication, so this interaction, so we just imagine that objects communicate by message passing. That is just imagination. Okay, yeah. So in practice, they are implemented by procedure calls. Okay, so while thinking, you just imagine there are 2 classes. One is say employee record, and another one is say student record, or any other, say, department record. Okay, so we imagine that they communicate through functions in each of them. Now the viewpoint is, so messages basically should be essentially name of the service requested by the calling object. So a function call is seen as service. Okay, so the employee record or a department database. So you just imagine these are 2 objects waiting for servicing. Okay, when you call, you basically pass a message through parameter, and then requesting service. You are basically requesting service. So for example, in graph, right, when you say graph.update, you're basically requesting service of the graph object to update. Update is the functionality. Okay, so that is a viewpoint that is taken. Yeah. So here, so this is, I mean, yeah, this just tells how it is done practically and how it is thought out abstractly. So abstractly, you say imagine them as communicating. In practice, it is through function calls or procedure calls. Okay. So this is an example. So if you want to call a method associated with the buffer object that returns the next value of the buffer, so you're calling this. This is how we do function calls, right, for a class object. And say call a method associated with the thermostat object that sets the temperature to be maintained. Thermostat.set temp. It's pretty much very consistent with C++ language. It's like I said, it's not exactly the same as C++ or Java, but very closely related. Okay, notations are fairly similar. So now we look at. So we have seen inheritance. We know what inheritance is. The terminology used by software designers or software engineering people is generalization. They don't use the term inheritance. Okay, so inheritance is something feature available in the programming languages. So, but the terminology used is called generalization. Okay, so objects are members of classes which define attribute types and operations. Classes may be arranged in a class hierarchy where one class is a generalization of one or more other classes. That means one class will be inherited. So it basically derives from one or more classes. So yeah, so the generalization is a terminology used for inheritance. Okay, I mean the terminology used in the UML as well as UML as well as the O research community. Okay. Okay. So we have seen advantages of inheritance or generalization. I'll also touch upon what are the limitations. Okay. Yeah. Okay. So this is an example. Before that, this is an example of inheritance structure. We have already seen this kind of thing. So employee, then manager is an employee, but with the additional feature. Programmer is an employee, and again among managers there could be department manager of projects or department manager of say just managing the departments or strategic manager. It could be anything. Okay, so this is how the hierarchy looks like. So employee, manager derives from it, programmer derives from it, project manager derives from manager, department manager derives from manager, strategic manager derives from manager. Okay, so this is the generalization structure, which we basically called as inheritance. Okay, yeah, so there are multiple views on inheritance. I'll just describe this briefly. Okay, so one is the limitations of inheritance. We have already seen advantages of inheritance, right? I've already asked many of you questions about advantages of inheritance in the mid-sem viva. Okay, so but there are also limitations. Okay, so one major limitation is this inheritance or generalization makes the classes not self-contained. Okay, so when you're inheriting, say for example, the string class. Okay, so your new class will not be self-contained. If somebody wants to analyze, that person should also know what is string class. Okay, so that is one limitation of inheritance. It's a question. No. So Madhav, so the question is generalization the opposite of inheritance? Not really. So inheritance is basically generalization. So you have a base class, you generalize it. It's basically inheritance. Okay. Yeah. So the terminology used is generalization. Okay. Inheritance is the terminology used in most of the programming languages. Sorry. Go back. Inheritance, I mean, generalization is the terminology used in UML. That's all. Okay. No. Okay. So that way, yes. That way, I agree. Base can. I don't know. Okay. Yeah, if you use that, that viewpoint, I mean, more general means more broad, you mean, right? Yeah, that's probably true. Okay, I'm not very familiar with that. Yeah. Yeah. Yeah, I agree with that. Okay. I mean, yeah, generalization is something you, yeah, that is true. That is true. If you, yeah, it's the opposite of inheritances. You're right. Yeah. So here itself, employee is the most general. Most general. These are the specific ones. Yeah. Yeah. Thank you for the question. Any other questions? Yeah, inheritance is, I mean, sequence wise, it is the opposite. Okay. So here employee is a generalization of manager. Manager is an inherited. Manager is a derived class of employee. Okay. Yeah. That's a good point, Madhav. Any other question? Okay. Yeah, so these are limitations. So designers have a tendency to reuse the inheritance graph created during analysis, can lead to significant inefficiency. The inheritance graphs of analysis, design, and implementation have different functions and should be separately maintained. And this is specific to software development people. So when you, I mean, see, inheritance, you can always imagine it as something useful feature, but doing it every time, right, may not be really productive or useful as such, basically due to these reasons. So you have to be like critic of when to use inheritance or generalization and when not to use. Okay, so yeah. So, like I had mentioned, object-oriented design essentially spells out different classes or class objects, then interactions between them. So in UML, it is called association. Okay. So if you have multiple classes, the relationships among them is called UML association. In UML, it is called association or class association. Okay. And the inheritance or generalization structure, in UML, it is actually treated as an association. Okay. But association will also tell what association is it. Is it inheritance or generalization, or is it just communication? Okay. So typically, associations will be annotated with information that describes the association. Well, there are of course different types of associations. We'll see in the next slide with an example. Usually these are generic or general. Okay, may indicate the attribute of an object as an associated object, or a method relies on an associated object. Okay, so for example, this is an association model. So we have three classes: employee, department, and manager. Okay, so the association is mentioned by this relation. So employee is a member of department. Employee is managed by a manager. Manager manages him. So it's naturally not symmetric, need not be symmetric. Okay, so associations are basically relationship between classes and usually specified by an adjective which describes the association. Okay, so is managed by, but here it really does not say that manager is a derived. So you can add additional. So manager is uh, an inherited class from employee, or employee is a generalization of manager. Okay, so yeah, so this example does not specify that detail, but this is one yeah, way of doing it. Okay. Yeah, any questions? Yeah. So another feature here in object-oriented programming is so we can view these objects as concurrent objects. Okay, so you can see each object is acting on its own. Yeah. So the imagination is make objects are self-contained entities, make them suitable for concurrent implementation. That means it makes so yeah, I don't know. Yeah, very unlikely that you have seen concurrent programming or concurrent implementation. Okay, so see there are multiple things. Okay, so the moment you make object views, suppose you have a team. Okay, say a team of 20 members. Say you have 5 objects. So now you can divide this team into sub teams of 4 members each. Okay, you can ask them to implement each of the classes, that is functionalities for each of the classes. The moment you have the design, right, the interaction and so on specified, so all you have to do is you need to have consistency. I mean, in the sense that the data type of the parameters being called and passed should be the same. That is specified in UML. Okay, so the moment you have that, it allows us to make concurrent implementation. That is, implementation can be done parallel. Okay, well, in sequential, I mean, in the traditional imperative programming too, you can do when you describe this as functions, but objects makes it more systematic. Okay, and yeah, so this is the software development view. The second view is the concurrency is actually in running. Okay, so you can also imagine each object is running possibly on a different processor or a different system. They communicate with each other, so they're implementing their functionalities. Whenever one object calls a method of the other, so that is when the communication happens. So that is the sequential dependency. Modulo that, all their inner attributes, inner things, right, inner implementations, which does not require communication or management of data, they can do on their own. Okay, so there are 2 types of concurrency. One is in the development, that is software development. While developing each individual, you can subdivide this into development of classes for a group of people. Then each group can come up with their own implementation parallelly. Second thing is while the program is being run. Okay, so the program is being run, you don't have to see it as one program being run on a single system. You can just imagine each class object is running on a different system and they communicate. So there is that kind of concurrency or parallelism there. Okay, this again more abstract. I'm not giving specific examples here. Yeah, so what I do is next, I have 5-10 minutes. Yeah, 10 minutes. Okay, so the next 10 minutes, I just quickly go through this again due to Somerville. I won't give full details, but at least a rough idea of. So design for a weather station. Okay, so you can just imagine a weather station. You want a software package, which also involves instruments which are controlled. Okay, So it consists of instruments which collect data, perform some data processing, and transmits this data for further processing. Okay. So here again, let's suppose the instruments include air and ground thermometers, anemometer, a wind vane, barometer, and a rain gauge, suppose. Okay. So, and we can imagine that data is collected every 5 minutes. Now, so what are the requirements? So what is the server view? So this basically is the data that it needs to process. Okay. What are the requirements? Whenever a command is issued to transmit the weather data, the weather station processes and summarizes the collected data. The summarized data is transmitted to the mapping computer when a request is received. So you can just basically your function output of the function, you can just imagine that's the transmitted data. Okay. So let's just quickly see how to develop an object-oriented system. I'm only going to give a part, only the object-oriented design part. I will not see the sequence diagrams and so on. Okay. So the first step is you develop architecture. You identify subsystems. Okay. So the subsystems, this is basically done by Somerville. Identified here are, one is data display. So data display layer where objects concerned with preparing and presenting data in a human readable form. Okay, so that's basically the user interface or the display, let's call it as. The second part is data archiving. That is, objects concerned here will be concerned with storing data for future processing. Basically, your data structure. Okay, so data archiving is your data structure or database. Okay, so data processing is you're basically looking at the archived data. You want to say you might want to check certain conditions or integrating the collected data or analyzing the collected data. Okay, and the data collection layer should be basically collecting data from the sources. So sources are the devices that are implemented. I mean, data that are to be installed. Okay. Yeah, finer view will be this. Okay. So the data collection from different sources, could be balloon, from weather station, satellite, or other observatories. Okay. So data display will consist of user interface, map display, could be map printer, which again, so these are all identified objects. Okay. So user interface object interacts with display object, map interacts with the map display as well as map printer. Okay. So these are, their purpose is basically to store maybe weather map or whatever, and user interface is basically interact with the user. And the data processing you can subdivide into classes, data checking and data integration. For data archiving, so there is this data storage class which stores data. You can just imagine it's a database. Then which again subdivided or so that as derived classes, maybe map store, data store, or maybe other features actually. This is just one example. Okay, so this is the coarser view. We created an architecture, so that is basically identified subsystems with their specification. What is their functionality in human readable form, of course. Yeah, and these are all readable for us, not programmers right away. And then we made a finer view. This is something that can be implemented in UML or written in UML. You have basically classes or meta classes, and within that you have identified classes and their interaction. So these edges basically say association. We didn't name the association here right now. Yeah. So this is another way of viewing our architecture. Okay. Now the next step is we need to identify classes. So how do we identify classes? So here there is a rough identification that happens, but still these are not concrete classes. Okay. In most of our assignments, the task was very easy because we already said, okay, define this class. Okay, so there is nothing to identify. And some of you, I had even asked Viva question. Okay, so what is a class? What will you have class, or what is a inheritance structure that you can have? But again, they are very, very narrow. I mean, mostly restricted to graphs or matrices. Okay, so in general, object classes, there may not be such specification, and of course, there is no magic formula for their identification. It mostly relies on the skill and experience or possibly domain knowledge of the system designers. Okay, and it could also be an iterative process. That means you come up with a set of objects, then you go to implementers or go to users. Maybe the requirements could be different. You may have to come up with more finer or more detailed classes. Okay, so yeah. So different approaches for object identification is just look at the natural description of the system. So that is what we did here. Okay, so we just took the finer view. So based on whatever the description was there, so we basically identified the classes. Okay, there are also other ways. Yeah, identification of tangible things in the application domain. Use a behavioral approach and identify objects based on what participates in what behavior. Or scenario-based analysis. The objects, attributes, and methods in each scenario are identified. Okay. I'll not really go into the details of this. I mean, this is not relevant for us. I mean, it's just to tell you that apart from just writing a program and implementing it, there is a design view which actually particularly useful. I mean, necessary, not just useful, when you have big software systems, when you want to build bigger software systems. Okay. So here, I mean, I'm just following what Somerville did. So the identification of the objects would be objects for each of the equipments that you have, that is ground thermometer, anemometer, and barometer. So application domain objects that are hardware objects related to the instruments in the system. Then weather station. So basic interface of the weather station to its environment. Whoever the weather station needs to communicate, whatever other softwares it needs to communicate or other systems it needs to communicate. So it basically reflects the interactions identified in the use case model. Okay, so we haven't said what use case model is. Usually use case model is based on the utility. Okay, yeah. So yeah, let me not really get into that right now. And then possibly a meta class will be weather data. You want to store the summarized data from the instruments. Okay, so this is one way of identifying the classes. So this is how it will look like. So in the UML specification would look like weather station. You basically describe the maps as well as the data. Maps here as well as data. Maps and data. Data here, map. Data here and map. Okay. Yeah. So yeah, one exercise I would like you to do is like whenever you have free time is to try drawing interaction diagram. Okay, so tell what are these associations between these classes and so on. Okay. Yeah. So I have skipped a lot of details here. In fact, there are also terminologies. I didn't really describe what is use case model and so on. Yeah, we'll not be able to do it right now. This is a terminology from software engineering domain. Okay, so yeah, so this is again something I'll not really describe. So you can, I mean, this is another way of like refining your classes, identifying objects. Okay, so you talk about active or passive classes, or use domain knowledge to identify more sub objects and so on, or more operations and so on. Okay, so yeah, so one more thing that is important here is design model. Once you have identified the classes, so you need to describe their structure. So static structure is the relationships, that is associations. Dynamic is something basically flowchart. That is which method will be called first and how the sequencing goes and what are the loops. Okay. So this is again one view that is given in Somerville. Okay, so weather system. So if you just look at the weather substation, the model might look like this. Okay, so these are instruments, this is the interface and data collection, and these are the interactions. Again, the interactions are not labeled yet. Okay. Yeah. So there are also other models that are needed many a times, particularly. So this is object model, that is like classes standalone and their interactions, and then the sequence model, that is sequence of object interactions that takes place, basically flowchart. Okay, and an equivalent or another alternative is to have state chart, that is you describe states of the system and how they move. So you must be very familiar. I mean, those who are from CS or doing the LMC course, right? So you have this finite state systems, which is BFA or push-down automata, right? They are described through state diagrams, right? So similarly, for your software system, you identify states and then describe diagrams. And so there are also other dynamic models which describe the dynamic interaction other than state charts. Okay, so we'll not go into the details. Yeah. So just to summarize, so our purpose was to just to tell you that apart from what you have done, which is like one leg of object-oriented system development, which is basically object-oriented programming, there are two more layers, which is object-oriented analysis and design, okay, which also play important role in particular developing large systems, okay, and yeah, so there are some features, some description of classes and ways of describing your system using UML, and how do we describe interactions and how do we sequence and so on. Okay. Yeah. So these are the summary. Some of the details I have skipped, and many of the details I have skipped. So what you have is one weapon, that is the object-oriented programming. So I request you, whoever is doing an internship, a system development internship, that is maybe a web development or a program development, I request you to spend some time on, say, software engineering book by Ian Somerville. This not only does object-oriented, this also does non-object-oriented. Or a book by Grady Booch et al. This is specifically about object-oriented analysis. Okay. So parallel to your internship, read this book and try to see your project work in this perspective. I believe most of you will be like having a development work right now, because you are yet to do many more core courses, right? Your internships might be a software development work, is what I believe. So those who have that, I request you to do that. This will certainly help. So one unfortunate thing is we don't have a software engineering course in the department anymore as a core course. And since it's removed as core course, I don't think it is being offered. Okay. This is kind of a handicap, particularly though for those who want to pursue software engineering career or career as a software engineer. Okay. Because you will be working in huge projects, then you need these kinds of abstractions, okay, or formalisms. In fact, many of the companies even would teach you all this in the training period. I don't know. I mean, it depends on the kind of company, I believe. But my suggestion is, so spend some time reading. So now that you have programming skills, I hope all of you have good programming skills already. So in the next semester, you will also be seeing a completely different view on programming. That is through what we call as paradigms of programming. So what we have right now seen is imperative programming, and an offshoot of it is through object-oriented programming. We have done object-oriented programming. We haven't done the design part of it. In the next course, CS3100, you will be looking at 3100 or 330, okay, whatever, paradigms of programming. You will be looking at other paradigms. Okay, so there is something called functional paradigm as well as logical paradigm or logic program. So these are completely different ways of thinking about programming. So to complement the viewpoint that you develop there, I request you to read, say, software engineering or object-oriented analysis. These two are suggested books, but there are plenty of other books. Okay, so that you will be a perfect software engineer when you are out of third year. Okay, yeah. So with that, I'll stop. So there are two more assignments. This is the 8th assignment, 9 and 10. After that, I'll have a brief meeting regarding the end sem. So the end sem will be basically, like I mentioned in the last lecture, 2 questions will be there. One will be like implementation of an algorithm. The other one might also involve a bit of program problem solving. Okay. Yeah. So that is all. Yeah, I know that. I mean, this is fairly abstract, and I also must admit that I'm talking about this or thinking about object. I mean, this kind of abstraction after 20 years, in fact. Okay, so yeah, when I was taught during my undergrad, software engineering as well as object-oriented, we in fact had 2 courses for this. Okay, so some of the terminology and all, it's not that what do you say, accent over for me. Okay, so need to, yeah, it's not immediate. Okay, so I hope you'll take motivation. So see, the purpose of the course was basically to train you in. Oh, sorry, there was a typo. So train you in object-oriented programming, but it is complete only when you also know what is object-oriented analysis and design. Okay, so yeah, so that part, this course is insufficient because that's majorly theoretical. Okay, so and like I said, for I don't know the reason, but somehow our department decided to. I mean, the idea was basically to have it as soft core, but unfortunately, it's not being offered anymore. Any of the, I mean, software engineering course or object-oriented design course. And of course, I am not an expert. So. Okay, any questions? I will stop the recording.